Annoyed by slow loading websites during busy times? Frustrating, isn't it? Well, there is a secret weapon companies use to stay speedy: caching. In today's video, we are going to cover almost everything about caching, including its benefits, caching strategies, cache invalidation methods, cache eviction policies, and solutions to some common cache related problems. It's going to be a lot of learning and fun learning. So keep watching till the end. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. In today's world, users expect lightning fast website, but as the traffic peaks, the performance can suffer, and that's where caching comes in. Consider a popular e-commerce platform experiencing a surge in user traffic during a festive season sale. As the number of users increase, so does the volume of database queries, resulting in sluggish performance and delayed response times. This performance degradation impacts the user experience and may lead to lost sales opportunities for the business. To mitigate the performance issues caused by increased database queries, the e commerce platform decides to implement caching. By caching frequently accessed information such as product details, prices, and availability, the platform aims to reduce the database queries and deliver faster response time to users browsing the website or making purchases. But will the caching really help the e commerce platform mitigate the performance issue? Let's understand how caching works. When a user visits the e commerce platform to view product listings, the system first checks the cache for the requested product information. If the data is found in the cache, it is retrieved quickly and served to the user, resulting in a seamless browsing experience. However, if the data is not present in the cache, the system retrieves the information from the database, serves it to the user, and updates the cache to prevent future incidents of not finding the data in the cache. If the data is found in the cache, it is called cache hit, and if not, it is called cache miss. But how does the desired data get loaded to the cache? And how do we ensure synchronization between the cache and the database? There are several caching strategies that help us keep the data in sync. Let's explore them. Caching strategies are the approaches to manage how data is stored and retrieved in a cache. Let's understand few commonly used caching strategies. In a read-through caching approach, when a cache miss occurs, the system automatically fetches the data from the database, updates the cache, and returns the data to the user. Using memcached for caching of frequently accessed database queries in a web application is an example of read-through cache. In cache-aside caching, when a cache miss occurs, the application directly fetches the data from the database, updates the cache, and returns the result to the user. MongoDB caching frequently accessed user profiles in a social media platform is an example of this caching. With write back caching, data is returned to the cache first and then asynchronously returned to the underlying storage at a later time. This strategy improves write performance by reducing the latency associated with synchronous disk writes. A database system caching write operations in memory before committing them to disk to improve overall system responsiveness and throughput is an example of this caching. In write aside caching strategy, the data is directly returned to the underlying storage without being cached initially. Only subsequent read requests for the same data trigger caching. This approach is beneficial for data with low access frequency or data that does not benefit from caching. An example of this caching would be a file storage system where large files are written directly to disk without being cached. to optimize cache utilization for frequently accessed files. In write through cache, every write operation to the database is also written to the cache simultaneously. This ensures that the cache is always up to date with the latest data. Redis cache with write through caching for user session management is an example of this. Okay, now that we have loaded the data in the cache, how do we ensure that it is still valid and not outdated? Cache invalidation methods confirm that the cached data is in sync with the original source. Cache invalidation is the process of removing or updating the cache data when it becomes outdated. This ensures the accuracy of the cache data. Cache invalidation methods are broadly classified into two: time based invalidation and event based invalidation. Let's understand each of them in detail. Time to live expiration is a time based invalidation method. This method involves setting a time to live value for cached content, after which the content is considered stale and must be refreshed. When a request is received for the content, the cache checks the time to live value and serves the cached content only if the value has not expired. If the value has expired, the cache fetches the latest version of the content from the origin server and caches it. For example, in a news application, articles in the cache may have a TTL of 24 hours. After 24 hours, the articles expire and are removed from the cache. In event based invalidation, the cached entries are invalidated based on specific events or triggers, such as data updates or deletions. Let's discuss some commonly used event based invalidation methods. The purge method removes the cached content for a specific object, URL, or a set of URLs. It is typically used when there is a change or update to the content and the cached version is no longer valid. When a purge request arrives, the cached content is removed immediately, and the next request for the content will be served directly from the origin server. Refresh method fetches a requested content from the origin server even if cached content is available. When a refresh request is received, the cached content is updated with the latest version from the origin server, ensuring that the content is up to date. Unlike a purge, a refresh request does not remove the existing cached content. Instead, it updates it with the latest version. The ban method invalidates the cached content based on a specific criteria, such as a URL pattern or a header. When a ban request is received, any cached content that matches the specified criteria is immediately removed, and any subsequent request for the content are served directly from the origin server. Stale while revalidate method is used in web browsers and CDNs to serve stale content from the cache while the content is being updated in the background. When a request is received for a piece of content, the cached version is immediately served to the user, and an asynchronous request is made to the origin server to fetch the latest version of the content. Once the latest version is available, the cached version is updated. This method ensures that the user is always served content quickly, even if the cached version is slightly outdated. After the cache invalidation, it appears that the cache is full and has latest data. But the cache misses have increased tremendously. So, what steps should be taken next? We need to make room for new entries in the cache and reduce cache misses. This process, known as cache eviction, is crucial for optimizing the cache performance. Cache eviction policies determine which items are selected for removal based on a certain criteria. Let's discuss few cache eviction policies. LRU removes the least recently accessed items when space is needed for new entries. For instance, In a web browser's cache using LRU, if the cache is full and a user visits a new web page, the least recently accessed page is removed to make room for the new one. MRU evicts the most recently accessed items to free up space when necessary. For instance, in a mobile app cache, when the cache is full and the user tries to access a new feature, the most recently accessed feature is evicted to accommodate the new data. In a first in first out cache, the oldest items are removed first when space is required. For example, in a messaging app, when the cache is full and a new message arrives, the oldest message in the cache is evicted. Least frequently used caching removes items that are accessed the least frequently. LFU keeps track of access frequency, and when space is limited, it removes items with the lowest access count. For example, in a search engine cache, less frequently searched queries may be evicted to make room for popular ones. Random replacement caching selects items for eviction without considering access patterns. For instance, in a gaming app cache, when new game assets are to be cached, RR randomly selects existing assets to replace. Each cache eviction policy has its advantages and disadvantages, and the choice depends on factors such as applications, access patterns, memory constraints, and performance requirements. The e-commerce platform in our example has now implemented a caching solution, leading to noticeable improvement in website performance. However, several cache-related issues have recently emerged. Cache-related problems occur due to issues such as multiple users or processors accessing data simultaneously, outdated cached data, limited cache size, network problems, incorrect cache configurations, implementation errors, dependencies on external systems, and inadequate cache forming strategies. Let's discuss solutions to few common cache related problems. Thunderbird problem occurs when multiple requests trigger simultaneously cache misses. This could happen when a large number of cached content expires at the same time. As the requests now directly hit the database, it overloads the database. There are two ways to mitigate this issue. One is to avoid setting the same expiry time for the keys. Another approach is to limit database access to essential business data only, preventing non essential data from accessing the database until the cache is operational again. Cache penetration happens when malicious users bombard the system with requests for non existent data. This causes a cache bypass and causes unnecessary load on the back end. One solution could be to implement input validation and rate limiting to mitigate the impact of cache penetration attacks on the system. The cache breakdown problem is similar to the Thunderhead problem. It happens when a hotkey expires. A large number of requests then directly hit the database, overwhelming the system. Since the hotkeys make up 80% of the queries, a solution to this problem is not to set an expiration time for them. Cache crash happens when the cache is down, either due to software bugs or hardware failures, and all the requests directly go to the database. There are two ways to solve this problem. One is to set up a circuit breaker, and when the cache is down, the application services cannot visit the cache or the database. The other is to set up a cluster for the cache to improve cache availability. In companies like Amazon, Netflix, Google, Meta, and eBay, caching solutions like Redis and Memcached are usually used for caching dynamic data, and CDNs are usually employed for caching static content. In summary, Caching is vital for optimizing the system performance in high traffic environments. I hope today's discussion will help you implement the right caching solution. If you found this video helpful, give us a thumbs up and subscribe to our channel for more interesting tech topics. Also, do check out our other videos on software performance optimization case studies, system design, big data, coding, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time.